In this module, we will be checking the drift as per ASCE 716, torsion irregularity and soft story checks as per the ASCE code. Drift is actually a difference between two interstories displacements, and when you measure that in unit, for example, in inches, you will call it as a drift. But when you calculate it by ratio, for example, there are no units, for example, 0.0018, so that is called drift ratio. And you obtain that by dividing the drift in inches or millimeter by the height of the story. So as per ASCE 716, the deflection at level x, they name it as delta x in inches and millimeter, and it is used to compute the design story drift delta, and it shall be equal to this equation, which is delta x is equal to CD into delta x. Means the elastic, the displacement that came from the linear elastic analysis, and I is the seismic importance factor. So if you have drift in inches and you have to multiply these with CD and you have to divide it with the importance factor, then you will get the drift in inches. But when you want to calculate it in terms of the ratio, this is the ratio that the allowable drift delta A for the different type of structures, and for our structure, it is for stress category 3, it is 0.015 HX. S, right? So the ratio is 0.015, which is 1.5%, the limitation. And when you multiply this limitation with the height of the story, you will get the limitation in inches. You can see that the drift limit for our building is 1.5%, and when you multiply feet into 12.44 with 0.015, you will get 0.16 inches. So if you want to calculate the drift in the displacement in inches, then you have to compare that inches with this one. It should be less than 1.6. But when you want to calculate it in the terms of the ratio, you have to, the ratio should be less than 0.015, 5%. So this is the different table you can use for the risk category 1, 2, 3, and 4. And these are the limitations. For example, for the hospital, it comes in the risk category 4, the allowable story drift limit is 1%. Right? So these are the different limitations. You can use it as per your requirement. In ETABS, you have to follow the path that is shown as below. Then you have to go to the display, show tables, analysis results, joint displacement, and click on the story drift. And then you have to insert these values in the Excel sheet, and Excel sheet will indicate you whether there is a drift controlled or not controlled in the desired direction. So if there is no drift issue, then you can move on towards the design and you can perform other checks as well. So let me go to the E tab. Previously, in the last lecture, when I was trying to reverse the 3-axis, it is actually not from the assign menu. You can select, for example, this is the shell, and go to the edit shell and click on the reverse wall local 3-axis. So this is the way you can reverse the local 3-axis for the shell. So this was the point which I remembered last time. And I told you I will show you in the next lecture. So before checking the story drifts in the table, you have to define a load pattern, and it will be EQX drift in X direction and EQ in the Y direction. And for that, let me define it. For example, EQQX drift, and click on the type as seismic drift, add new load, and select load, modify, and the modify lateral load. Then you have to define or insert the values that you have inserted in the QX, which is really the type is seismic. The same data shall be inserted in the seismic drift. Actually, the code give you a relaxation in terms of calculating the drift, that is the difference between this seismic and this seismic drift. That in this seismic, there is limitation on the time period and the minimum base shear, but in the seismic drift, there is no limitation on the minimum base shear and the time period. So when you calculate the base shear from the EQX, it will be a bit higher than the calculation that you have done calculation for the seismic drift. You will see that. And after defining for the both of the both patterns, for example, this is EQX drift in the X direction, same values that we have defined for the X simple, and Y drift for the Y direction in the same seismic parameters. And then you have to run the analysis. Right? So let me go to the analyzed model. And then let me show you the base shears. This is structure out base shear, and then select the loads to X drift Y, and then select the load cases these two and these two. And then you will clearly see that you can see that this is the FX, this is the base shear X, which is 6988, right? And for the EQX drift, the base shear is a bit less, which is 6602. There is no restriction on the minimum base shear and the upper limit of the time period. So we will go to the table again, and we will check this. We will click on the analysis results, join output, displacements, and click on the story drift. We will select the load pattern only EQX drift in EQY drift. This is the load patterns, and load cases will be only these drifts. And we will select none the load combination, and we will click OK. Right, so you will get this table. Let me go to the presentation. Why is it not working? I think look this. So for the drift check, when you take those values from the table, we will again go to this table and we will extract those values. So when the drift is not within the code allowable limits, then you can perform the following changes to reduce the drift. You can see that in the calculation that this is the story levels. This is the drift in X direction, drift in Y direction. And the Excel sheet will calculate the delta M, which is the elastic displacement, and it will compare it. I have done it programming in it. it will compare with the allowable limit, which is 1.5% or 0.015 drift ratio, and it will give you an indication that the story drift in the x direction is controlled or not controlled. Similarly, the drift ratio drift limitation in the y direction is controlled or not controlled. So we'll come towards the different consequences and mitigation measurements that we can perform during the analysis. So again, we will go to the table. Select the story ranges from first basement to the top floor without the Monty, and in load case only select X shift and select the step equal to 1 or 3 or 2. The results will be the same, and direction only X. So this is the drift ratios, because it can give you result in terms of drift ratio. Then you have to compare it with the drift ratio in the table as per the ASCE. You have to select all the drift ratio for all of the stories, Control C, and click on the Excel sheet and insert these values, Control V. We can see that by inserting the ETABS values gives you indication that the drift is not controlled beyond the fourth story, right? The X direction. Up to third story, the drift is controlled. Similarly, for the Y direction, again, click on this down, select this time Y. The step number is equal to 1, and the direction this time Y. Again, copy this, Control C. And insert this value in the Y column. The drift is not controlled in the Y direction in the second floor, right? And in the X direction, it is controlled from the fourth floor. So, in order to reduce the drift or bring the drift within the allowable code limits, you can increase the left wall thicknesses, you can increase shear wall thicknesses, you can add more core walls and shear walls, you can increase number of columns, increase sizes of the columns, increase depth of the beam, and you can also increase the concrete compressive strength. Whatever is convenient to you, and it allows you the architectural drawings, then you can perform any of these. So to control the drift, we have I have done the following changes: that the lift wall thicknesses are increased to 21 inches from 18 inches, and the shear wall thicknesses are increased up to 24 inches. And we have also included new core walls and shear walls in our building, because the limit in the new code is too much conservative, and normally the structures are not economical, right? Which I have explained it earlier at the start of the course. And so this is the old plan in which we have walls and so So I had these things. So this is the x direction and this is the y direction. What you have to do, you can perform different trials that you insert the shear walls and core walls in the x direction and then in the y direction. Then you have to again check the drift limits. If it is not controlled, again you have to make changes, increase the thicknesses, add new shear walls, increase the column sizes, increase FC prime, increase beam depth. And in this way, with different trials, you can achieve the desired code. This is the end. After several trials, the drift became within the code limits. I have done that I have added this wall, the y direction, this wall, this is the actually complete core wall, which is the staircase. And similarly, this is the staircase. I have added this core wall and I have added this wall and I have also increased the wall thicknesses. And I have done different several trials, and after different trials, the drift are within the code limits. So we will check it out. We will go to the display show tables. And this is not the structure of code, joint output, joint displacement, story, drifts, load pattern is drift x, drift y, and drift x, drift load combination are 0. Set the story ranges again, only x drift, the only 1. In the x direction, and again copy these drift values, Control C, and insert in the x column. You can see that the story drift in the x direction has been controlled. Similarly, for the y direction, select the columns, Control C, and insert in the y column. And the it is now controlled in the y direction as well. So this is how you will control your drift with the addition of different walls and increase the sizes and thicknesses. Let me go to the presentation. We have done these. At the end of the course, I will share the complete final model with you guys. So this was the whole story about the drift check, that how the drift is checked using the tabs results, and how you can control the drift when the drift is not in the allowable limits. Next important check is the torsion irregularity, which is normally we have in each and every building, which is not regular. The torsion irregularity as per the C716 table 12.3-2, but I have only added these two statements that the torsion irregularity exists in the building with the maximum story drift computed including extended torsion with AX, which is the torsion amplification factor, which is normally taken as 1 at the